Week 6 is on capacitance in AC circuits. This is Unit 21 in the 6th edition, and it's Unit 20 in the 7th edition. We're going to look at why current appears to flow through a capacitor. It actually does not flow through the capacitor, but we're going to take a look at that in an AC circuit. We're going to talk about capacitive reactance. This is very similar to inductive reactance. We're going to figure out how to calculate the value of capacitive reactance in an AC circuit. We're going to figure out how to calculate the capacitance of a capacitor in an AC circuit. And then we're going to look at the relationship between voltage and current in a purely capacitive circuit. So we learned last week that capacitors are made up of two metal plates that are separated by a dielectric. There is no complete circuit between the plates. Current cannot actually flow through the capacitor because there is no complete circuit. In the circuit itself, the only time current can flow is when the capacitor is being charged or discharged. Current is flowing in the circuit, but it is not flowing through the capacitor. So when we have a capacitor connected to an AC circuit, it looks like current is flowing. But we're going to see as we go through these slides that current is flowing in the circuit, but not through the capacitor itself. So this is an analogy where we have two tanks that are separated from each other, tank A and tank B. The only connection that they have is through this pump here. So let's pretend that tank A is completely filled at time 0, and at time 0 tank B is completely empty. So when the pump starts, it takes the fluid, it pumps the fluid out of tank A into tank B. And after some time, tank B is completely filled, while tank A is completely empty. So capacitors in a capacitive circuit behave in a very similar way. When one plate is being charged positively, the other plate is being charged negatively. And then when the voltage changes polarity, the applied voltage changes polarity, then the first plate is being charged negatively while the second plate is being charged positively. It literally just goes back and forth. During the charging, that's when current is flowing through the circuit. And then when it changes directions, the current flows the other way. As the capacitor is being charged, an impressed voltage is developed across the plates, and that's built up as an electrostatic charge. The impressed voltage is the voltage provided by that actual electrostatic charge. This impressed voltage, or this counter voltage, opposes the applied voltage, and therefore it limits the flow of current. So there is a current limiting effect. This is very similar to how inductors work. This counter voltage developed by the capacitor is called reactance. And because the counter voltage is created by a capacitor, we call this capacitive reactance. Capacitive reactance is current limiting, and therefore it is measured in ohms. So here we see the formula for capacitive reactance. It looks similar to inductive reactance, but we see here we have a division symbol here. So I'm going to rewrite this. Hopefully the pen cooperates here. So capacitive reactance equals 1 over 2 pi frequency times the capacitance in farads. This is another form of that same formula, but we have a little bit of algebra. So if we know the capacitive reactance, but we do not know the capacitance of the capacitor, then we have this formula here. This is shown in, actually I'm not sure it's shown in Appendix B. I think the regular version, this version is shown in Appendix B. So I'm going to do the algebra here. So this is the formula that we saw on the previous slide. This is the formula that is in Appendix B. But instead of solving for capacitive reactance, we're going to solve for capacitance. So with an equation, to do the algebra, anything we do on one side of the equation, we must do on the other side of the equation for the equation to remain equal. So what I want to do is get C all by itself on one side of the equation. So I'm going to multiply the right side by 2 pi f. Whatever I do on one side of the equation, I have to do on the other side of the equation. So I'm going to multiply the left side by 2 pi f. This 2 pi f cancels this 2 pi f. So we end up with 1 over capacitance equals 2 pi frequency times capacitive reactance. If I rewrite that, so C is on top. So basically I'm going to put the C on the left side. Capacitance equals 1 over 2 pi f, or frequency, times capacitive reactance. So here we have a graph that shows the relationship between voltage and current in a purely capacitive circuit. So this line here, that's the applied voltage. This red line that is in phase with the applied voltage, that's the charge on the capacitor, and we see that they are in phase. And then this last curve here is the current flowing through the circuit. Again, current does not flow through a capacitor, but current does flow within the circuit. At 0 degrees, the applied voltage is 0, therefore the capacitor is not charged. And because of, we saw on the previous slide the math, because the voltage is 0, there is no capacitive reactance at that time, so the current limiting effect is not present, so therefore current is maximum at 0 degrees. At 90 degrees, the applied voltage is maximum. The charge on the capacitor is therefore also maximum. And at that point in time, the current limiting effect is greatest. So the current at 90 degrees is 0. At 180 degrees, again, the applied voltage is 0, the charge on the capacitor is 0, the current limiting effect is not present, therefore the current is maximum at 180 degrees. It's negative this time. At 270, it's kind of similar to at 90 degrees. The applied voltage is maximum, the charge on the capacitor is maximum, the capacitive reactance or the current limiting effect is maximum, so therefore the current is 0. So we saw on the previous slide that the applied voltage and the impressed voltage, or I'm sorry, the charge on the capacitor are in phase. That charge on the capacitor creates an impressed voltage, and that impressed voltage is 180 degrees out of phase. It's literally opposite of the applied voltage. So power in a pure capacitive circuit, it's reactive power. Again, very similar to with the inductors. It's also measured in bars, volt, amps, reactive. Now, we're not going to cover this, but if we did have a capacitive inductive circuit, the VARs, the capacitive VARs, and the inductive VARs are 180 degrees out of phase with each other. Similar to inductors, in a pure capacitive circuit, there is no true power. Again, in a pure capacitive circuit, there is no true power or watts. And it's because of that phase difference between voltage and current. Basically, they kind of cancel each other out. And this part of the slide is simply showing what we talked about in the previous slide. Inductive VARs are 180 degrees out of phase with capacitive VARs. With the quality of a capacitor, generally it is very, very high. It's the ratio of resistance over capacitive reactance. The resistance for a capacitor, that's the resistance of the dielectric. And we know that current does not flow through the dielectric. That means that the resistance of the dielectric is very, very high. So if we have a very, very high resistance and divided by something relatively low, a big number divided by a small number is going to yield a big number. Capacitors have voltage ratings, and the voltage rating of a capacitor is actually the voltage rating of the dielectric. If the applied voltage is greater than the particular dielectric can handle, the dielectric can break down. Just as a side note, there are no set standards concerning how voltage ratings are marked. They can be in AC volts, DC volts, peak volts, or working volts. So capacitive reactance, that is the current limiting effect of a capacitor, and it's inversely proportional to frequency. We saw with inductors that inductive reactance is proportional or directly proportional to frequency. Capacitive reactance is inversely proportional to frequency. So as the frequency increases, capacitive reactance decreases. I'm going to skip by this slide here and get directly to this slide. Here we're looking at the rate of how quickly the capacitor is charging in relation to frequency. So if we have two identical capacitors in these two circuits, the top circuit is at 30 Hertz, the bottom circuit is at 60 Hertz. With the 30 Hertz version, the capacitor charges up, basically it charges once per second. Don't worry too much about this coulomb here, it's a unit of charge. With the 60 Hertz version, we can see that the capacitor is charging twice as fast. It's at double the rate. So in summary, when a capacitor is connected to an AC circuit, it looks like current is flowing through the capacitor. It's not. Current should not flow through a capacitor. If current flows through a capacitor, that means the capacitor is bad. It's broken down. The dielectric is broken down. This appearance of current flowing in an AC circuit, it's because the voltage is constantly going up and down and it changes polarity. When current flows in a purely capacitive circuit, the current limiting effect is called capacitive reactance. It's measured in ohms, and we saw in the earlier slide that capacitive reactance is inversely proportional to the line frequency. And we saw with the math earlier, it's also inversely proportional to the capacitance of the capacitor. In a pure capacitive circuit, current and voltage are out of phase by 90 degrees. It so happens that current, this is circuit current, leads the applied voltage by 90 degrees. Similar with inductive circuits, in a pure capacitive circuit, there is no true power, there is no watts. We do have capacitive power, it's reactive power. So capacitive circuits have reactive power that's measured in bars, volt, amps, reactive, same as in inductance. However, capacitive and inductive VARs are 180 degrees out of phase with each other. The quality of a capacitor is generally very, very high. It's the ratio of resistance to capacitive reactance. This resistance is the resistance of the dielectric, which should be, it needs to be very, very high because we don't want current flowing through the dielectric. Capacitors have voltage ratings. Yeah, we don't need to worry about this last one, but DC voltage rating for an AC capacitor, it indicates the peak value of voltage.